Let's take a look at how the temperature of a substance changes with a certain amount of heat input. So the good old standard for heat measurement comes from water, and the calorie is defined as the amount of heat you need to raise 1 gram of water 1 degree Celsius, and degrees Kelvin is equivalent because they're the same size degrees. So degrees Celsius or delta C or delta Kelvin, same thing. And it was discovered a couple centuries ago that there is an equivalent with the mechanical work we've been discussing previously. So our good old capital W can be transformed into heat or thermal energy. The units conversion is 1,000 calories is 4186 joules, and so we can box that up because that's both a units conversion and a statement of the unification of thermal physics and mechanical Newtonian physics. Kind of interesting that. So what we're going to do with this is we're going to raise the temperature of a substance. So we're going to use a symbol Q for that. So that's the symbol for heat transfer. I believe there's a bit of a conflict because that's also the symbol for fluid flow, but the contexts are completely different, so hopefully you can keep them separate in your head. So anyway, this is a symbol for heat transfer, and it's going to have units of joules. Our good old SI unit, and that is the unit. We generally, unless we convert it for convenience to calories or kilocalories, joules is it. So always use joules for your calculations because that's what's going to come in the tables. We're going to have some mass of substance. So we're going to have M for mass. We're going to have a change of temperature. And we're going to have a lowercase c. That's going to stand for something called the specific heat. So specific heat. This is a thing that's tabulated. And it's tabulated in table 14.1 in that table there. The units are going to be joules per kilogram dot degree Kelvin or degree Celsius, either one. Now, if you look in this table, down at the bottom, they've got we've got at the top they've got solids and liquids, and then at the bottom they've got pardon me, they got gases, and they've got two different symbols for the gases. They've got C with a V on it, that's for volume, and C with a P on it, that's for pressure. And CV is this specific heat at holding constant the volume of the gas. And this one is C where you hold the pressure constant when you make this measurement. It turns out for gases they're quite a bit different, but for ordinary substances they're about the same, so that's why you only get one number for the liquids and the solids, but you get two numbers for the gases. So gases will have two of these guys. If you're reading a problem statement, it's going to say what's what. All right, so there's our symbol mishmash, and of course it all compactifies quite nicely for our formula. So there's our formula to box up. So the heat transfer in joules is equal to the mass of the substance times its specific heat, and then multiplied by the change of temperature. So usually you'll know the mass, although I suppose you could concoct a problem where that was the unknown. But usually your unknown is going to be either the heat transferred or the change in temperature. And so basically it's just Q equal delta T with some stuff in the middle. So this is really by itself not a hard problem. They might disguise this mass in terms of a volume times a density. So keep in mind that that's our definition for density is a mass per unit volume, so we got to multiply by volume to get mass.